let's continue to the last topic, which is the network analysis. Have every one of you done some network analysis in ArcGIS? Yes? No? Well, now you will learn how to do it in Python. So the is the idea of routing and network analysis familiar for you, Cecilia? Is the idea of network analysis and routing familiar? Yes. Yes. So we don't need to go through that. But basically, yeah, so there are a lot of different tools available, like in general in GIS to do network analysis. I guess the most common one for us, at least our department, is to use the network analyst in ArcGIS. But that's not, of course, the only tool that's available. That's a pretty good one, though, and quite easy to use. But there are a lot of different tools. So Quantum GIS has some plugins that can do some simple network analysis. Then there is this PG routing for PostGIS, which is a database based routing engine and this kind of package, which is used a lot in web applications because it's basically running in database. So it's really nice to implement that and use in the different web services. We won't be using that, but we'll basically introduce how to use this Networkx functions and do these in Python. So basically what this Networkx package that I mentioned already earlier provides is different kind of algorithms to do the shortest path analysis, such as Dijkstra's algorithm, which is the most commonly used optimization kind of algorithm available. It's not the most efficient one because it always goes through the whole network when it does the routing. But then there is this A-star algorithm that is a bit kind of more efficient in a way. It doesn't, it kind of, yeah, well, it's more efficient, doesn't need to go through the whole network when it's doing the optimizations or the routings and so on. But anyway, so these algorithms are available in Python in this Networkx package. And what this Osmnx package that we just saw have done is that it has made it much easier to actually work with the network data and to work with Networkx, because like you saw, retrieving data from OpenStreetMap is as easy as we just saw. So it makes it quite nice to just fetch some road network data and start routing in anywhere. Let's continue. So the idea here, what we will do now, well, again, maybe I show you the final output so that you will see what we are aiming at. So what we are doing here is that we have a couple of points, so origin and destination point here, and then what we do is that we search the shortest path between these 2 points, now only based on the distance. Of course, we could, if we would have more time, we could basically kind of use the travel time as the impedance, basically taking the speed limits into account and so on. But now, just for the sake of time, we will only use the distance as the impedance or the cost value when using the routing here. So that's the goal, and let's see how we can actually reach that point. So I will create a new script for that. So network routing in Python, and let's save it here. Lesson 7, network routing. And again, what we will do, well, first of all, we import the necessary packages, well, the Osmnx being one of them. Then now, as I explained a couple of times already, the actual routing algorithms comes from this Networkx package, so we also import that. So import Networkx as NX, so this is the typical way of how we use that module, so we shorten it down to NX letters. Then what we want to do is that we import also GeoPandas, Matplotlib for doing the plotting in the end, and also pandas. So with these packages we are good to go, and I will now import those. And yeah, so let's start by same. So let's fetch the OpenStreetMap data from Compi. Now we just fetch it from Hell's Kitchen, so we need to do it again, but that doesn't matter, it doesn't take too long to do it. So let's say place name is Compi, Helsinki, Finland, and then let's fetch the graph, and we were able to do it by using this function graph from place, and we have the place name here, and let's do that. And let's, well, we already saw what the graph looks like, so it's somewhere here. So this is basically what we will get from when with the graph, so we don't need to visualize it again. Basically, yeah, now I show you. So here is the table basically explaining few of the different data types in the edges. So basically what kind of information is available of the street network. There are links, so for example the bridge, so we can basically take a look of the documentation in OpenStreetMap if it opens, like what is this bridge key tag in OpenStreetMap. And the highway is the kind of most important one in many cases. So there is a lot of information about what kind of different road types are available in OpenStreetMap, and basically, yeah, so you can go and take a look if you're interested and try to start to use these OpenStreetMap data. So take a look of those and check the documentation. Yeah, let's do first that we already did that part. Yeah, so let's see how we can project the data. So we have already seen what kind of attributes we have there, but in yeah, in this Osmnx there is this nice function that can do the projection for us automatically. So it will basically identify the UTM zone where the data is coming from. So in Finland we are at UTM zone 35, and what I mean by UTM is this universal what is it? UTM projection, let's take the English version. So it's this universal transverse Mercator coordinate system where the Earth is basically divided into different zones, and it presents the metric kind of system, so we have meters instead of latitude and longitudes. So what this OX can do is that it basically can project our data, the graph, and it will automatically identify the UTM zone of the data. So project the graph. So we can say that graph projection is ox.project graph. Of course, what we could do is that we basically convert that graph into geodata frames and basically do the projection there, and then basically convert it back to graph if we will, but this is a nice function that we can just use it directly. So project graph, and just specify that the graph is here, what we want to project, and it takes a couple of seconds, and now we should have the graph as projected. Let's plot so we can see that it has changed. So we can again use this fig x equals to ox.plot graph, and in here we now put, instead of the graph, we put the graph projected, and now we can get a better looking map of our data. So it's projected and it looks more appropriate to Finland, so it's not as twisted as these ones here, for example this. So you can see that it's kind of bending in north direction. Yep, so that's how we can do, and basically, yeah, we could take a look that if we convert those into geodata frames, we will see that also the values have been changing. But let's do so that let's continue and analyze our network a little bit. So as I said in the beginning, so this Osmnx package contains quite nice high-level functions to actually analyze also like what kind of properties we have in the network, or how does it look like from different perspectives. So let's say that calculate basic statistics of the street network. So when trying to kind of understand, so like what kind of properties our network has, it's useful to do this stats equals to ox dot, well, basic stats. And what we put here is that we put the graph pro, so this is our graph, and when executing this, and let's check what do we have. Well, we have quite a lot of information. So let's see if I can close this, as I won't be needing it. So what do we have here? So we have basically a lot of information, like how many intersections there are, what is the average edge length. So on average the kind of road elements tend to be 27 meters in this area. What is the total length of those streets on that area that we downloaded? Well, it seems to be, can it be right, 103 meters, 103 kilometers. So these are meters. Well, I guess it can be, I don't know. How many intersections there are? 1,185. Intersection density, of course, the function needs information about the area to be able to calculate the density, and so on. So there are some kind of missing information here. So let's take a look how we can actually calculate the area from that graph. So let's do so that calculate the area of the let's say, coverage area of the street network. So let's do so that I take the edges from that graph, OX, GDF, graph to GDFS, and I put my graph projected into here, and basically it's also possible to extract only the edges or only the nodes. So there are these parameters saying edges true, nodes true. So I can basically say that nodes is false, and in this case I will only get the edges. Well, let's say also that edges equals true. So now I should get only the edges from that graph, like this, and indeed I do have it. So now this is a geodata frame, and what I want to do is that I want to calculate what is the coverage area of this plot here, or this network here. And how we can do that is that what we are doing here is that we want to basically specify the convex hull of this area. So we need to basically kind of get and retrieve the minimum area of that of the street network. How we can do that is that, let's say, area equals 2. So what we are using the edges. What we need to do, we need to basically make a unary union out of these. So now we have a lot of basically different line strings. So what we want to have is that we make a unary union, and I will just show you what we have after that. So now we have this kind of geometry where it's a multi line string basically. So all the edges are kind of combined and merged together. So then after this we want to take the convex hull out of this. There is a function in Shapely called convex hull, and when we do this, let's take a look what happens. And again we have the area. Well, what we have now is that we actually have this polygon, and finally to get the area of this polygon, well, we just add dot area, and now we have the area of that in square meters, if I'm right. Yes, it should be in square meters. So this is how we got the area of that network coverage area, and now we can use the stats again, retrieve the missing statistics using the area information. So we can use the ox.basic stats, and we put the graph projected as an input graph in there, and then we specified what is the area. So one of the parameters that this function takes is the area, so we can say that the area is the area that we just calculated. And now we have more information, and now we have the node density per kilometer and so on, which is more information that we had before, and the edge density and so on. What we don't have here are different kind of centrality measures. So when we are analyzing networks, certain nodes and certain streets might be more important than the other ones. There are more traffic going through certain parts of the street network, and there are different measures that can actually give some kind of hints about this, and we can basically extract that kind of information with Osmnx or Networkx really, that is working in behind. So extract additional statistics. So let's say extended stats equals to ox dot extended stats. And similar story, we said that the graph pro is the one that we want to get the information from. Then there are these different parameters, ACC. Actually, I need to check what these are, but let's put them through. So I guess we get some more information by putting these parameters, but yeah, I don't now remember what they were. And by calculating the extended stats, we will get more information. It takes a while to actually calculate them. Shouldn't take too long. Then what we can do is that we can actually combine these two data sets or together. So I will just copy and paste. So what we are doing here is that we actually combine these stats that we are now calculating into the earlier ones and give them as a one long list of data. So I'll just copy and paste this. So what we are actually just doing is that we iterate over the items of that dictionary in the extended stats that came here. We can take a look. What does that look like? It might have a lot of information. So yeah, there is a lot of information here. So it might not be most reasonable to keep this information in this way. So what we will do is that we will combine now these statistics to the previous ones by doing this. So what we do here is that we iterate over each item and then we basically add that to the original one. And the final thing that we want to do is that we convert this dictionary into pandas series. That makes it much easier to read. So let's say stats equals to pandas series. Let's say PD stats, pandas series stats. And now when we call that, we get much easier looking table to read. And now we get these kind of different centrality measures. One of the interesting ones is, for example, the page rank centrality measure. How many of you are familiar with page rank? You use it every day, or at least you used to use it. It's the one what Google uses to order the kind of when you use the search engine. So how the results are ordered, it's based on this page rank algorithm or some kind of version of it. And that basically kind of what it does is that it tries to find the most important nodes from the network, and the network in the internet is basically all the websites and the links from one page to another. And the more one page has links coming into it, the more important it is. And that's how basically PageRank works. And what we have here is that we basically have kind of some measure for what is the maximum PageRank value of certain node. And then what is useful is that we actually even have the information that this node in the street network in Kamppi seems to be most important one, taking into account like how many links comes to there. So this is quite central node in a sense, and this can be quite useful information when analyzing street networks and so on. But yeah, there are more information in the website, and there is a kind of Wikipedia article about different centrality measures if you're interested in them. And well, there is some explanation about these different measures that we got. Yeah, there is a link to the Osmnx example repository. Actually, I could show it to you. So there is this kind of repository showing like all the tricks and stuff that you can do with this module. There is a lot of these kind of IPython notebooks that you can take a look and see. There are nice in kind of ways to visualize the data, visualize the importance of the kind of different nodes and networks, edges and so on. So recommend of taking a look of that. But then to the actual final topic. So how can we do the shortest path analysis using this network? This is the last thing that I will basically talk to you today. So maybe if you can last some 10 minutes longer, we can manage to do without a break today. But yeah, so network analysis is the topic now. So how can we do that? What we want to do in here in the lecture materials is that we want to calculate the route from the centroid of this network and to the easternmost point of this network. And we can basically, as we have this geometric information and the tricks that we have learned so far, so we can actually get the centroid point from this location, and we can quite easily get the easternmost point by just taking like from the nodes where the x coordinate is the largest. That must be the easternmost node. So that's how we can do it. First of all, this goes now a bit differently than in the lesson materials actually, but now as we have here the convex hull, so we can actually easily get the centroid of that. So instead of calculating the area, I will take the centroid of that place, and now I should have some kind of point. Yes, indeed. And it should have some kind of x and y coordinates. Indeed. So now basically what we are doing is that I want to use this as the source or destination location of my, this is the source location for the shortest path optimization. Calculate the centroid of the street network as the origin location. So that is that. I don't want to use that. What is this now? And then the other thing that we wanted to do is to get the target location, which should be the now we actually need to have also the nodes, because we want to get the easternmost node. So I make a simple change here. I said I also want to have the nodes. Yep, and now let's take a look. Nodes.head, and here we have the nodes, and we have the geometry, and we have the x and y coordinates. For some reason which I don't really know. The x coordinates here are integer values, whereas the y coordinates are a floating point. This might be a bug or some kind of feature of the Osmnx package, but anyway, we want to have these values as floating points to get the full accuracy of those. So what we need to do first is to convert those, convert x coordinates to floating point numbers. So we can say that nodes x equals to nodes. How can I do this? Help me. I want to convert these points into floating point numbers. Yes, as type float. So this is the trick we can do. And now let's take a look how our data looks like. And here we are. So now instead of having integer numbers, now we actually have the floating point numbers in here. And that's good. What we want to do next, as I explained, I want to know what is the easternmost location, and the x coordinate basically gives the information about is it west or east, and the bigger the number, the more east it is from the 0 meridian, and basically well, yeah. So what we want to do is to make a simple kind of query about the data frame where we actually are looking for the maximum value of this x column. So find the easternmost x coordinate and extract that row from the data frame. So first of all, we can basically get what is the max x value. We can say that nodes x dot max. So this way we can see that, okay, the maximum x value seems to be this number, and then what we want to do is that I want to select that row where the x number is this. So let's take that row. Let's say target location is nodes.log. So this is the way how we can query our data frame using the indices or the kind of different kind of queries. Then I can say that nodes x equals to max x, and then I want to have all the columns from that. How many of you are using this log function to make the queries in, or are you using the x? There are these different ways of doing things in pandas, because this seems to be now the one that pandas kind of hopes that people will use, this .log. And how this works is quite similar to how the other .dataframe.x works, but here you basically specify first the kind of query that you have. So here we are searching for nodes where the x column has the maximum x value that we asked or found out here. And then you put comma, and then you can specify what columns do you want to take from the data frame. And when you put the colon here, you will basically get all the columns from that data frame. So basically what this does is that now as I executed this, now we have this one column with the information about. So this is the easternmost node in our data frame that we have. Did you follow? Yeah, more or less. Okay, good. Then, so to recap what we are doing now, it seems to be complicated, but we want to search for origin and the destination point. Of course, we could have done it in a way that we just put some number and that would be it. But this is how we do it now, because after this we can basically do the same thing everywhere in the world. We can fetch data from Tallinn and do the same, get the centroid and basically get the easternmost point, and you will always get the root, which is nice. Yeah, so now we have the target point, and yeah, actually what we want to get from there, now we have the whole row, but what we want to do is that we want to have the geometry from that. So extract the geometry. So let's say the target point is this target location. So this is the whole row. So let's say that I want to take the geometry out of there, and if we do it like this, I will show you. Now what we have is that we have this kind of panda series out of this, but I don't want to do that. I want to have only the shapely geometry out of this. So how I can do that is that I take the values and I take the first value from this values list. So what this does is that it returns a list of the values from that series, and what I do is to take the first one. So now I should have the target point. It looks weird, but this is the shapely point object that we have now. And why do we do this? Is that what this routing algorithm and the functions want to have as an input parameters is the tuple of latitude and longitude values. So we need to extract the x and y coordinates from the from these points, so from the origin and destination points. So extract the coordinates from the OD points. So we can say that origin x and y is basically the so we want to have the centroid x and centroid y. So as we are actually using latitude and longitude, so it's always good to remember that we are actually putting the latitude is the centroid's y coordinate and the longitude is the centroid x coordinate. And the same thing for the other one. So the target x and y equals to a tuple of those coordinates. So target point dot y, target point dot x. And now we should have these kind of simple coordinate tuples, and the values should be different, and they are. And these we can now feed into the shortest path algorithm. The first thing that we need to do, I'll just show you the map here. So as you can see here, the first thing, because when we are calculating the route, we are actually calculating, we need to kind of find the closest node to the actual street network, and from there we can actually start doing the routing. So what we need to do first, this destination point, as we saw, it was the easternmost node. So that is actually a location which is already at the node, but the other one especially. So here we actually need to define which one of these is the closest node to the actual origin location. So we need to do that first before we can start doing the routing. So we need to extract, or well, find out the closest nodes from the network. So let's say that the origin node is, and again this package contains a nice function that can do just that. So OX get nearest node. So this is a function that basically takes as an input the graph that we have. So in this case we have the graph that was projected. So graph proj, and then what we put there is that we put the point, and as a point we now mean the origin x and y coordinates, oric x and y. And then there is this method that is by default create circle, which works basically with latitude and longitude values. But now, as we are using the metric system, as you remember, we projected our data into UTM, we need to specify that the method is not create circle, but it's Euclidean. And this is especially important because we can actually get out with this with this return dist. So if we put this true, we will also get the distance from the origin location to the nearest node, and that might be useful information for some purposes. Now we don't do anything with that information, so we just leave it out. But the method should be Euclidean so that everything goes correctly. And when we get and run this, doesn't take long. But what do we get out? Well, it's this kind of number. And what this number basically is, it's the OSM ID. So it's the ID of that node that was closest to this origin location that we had. And that's information that we can feed into the routing algorithm. And then the same thing for the target node. So OX get nearest node. We use the graph projected. Then we, instead of putting the origin x and y, we put the target x and y. And the method is Euclidean. And this way, oh, right, there is a typo, Euclidean. So now we also have the target node, and it seems to be this kind of number. Cool. So now, yeah. Now what we can do is that we can start doing the actual routing. So find out the shortest path. So how we can calculate the route is that we use now from this Networkx package a function called shortest path. And this is basically what we will need to do. So it's only one function that we can use to actually do this. Now we need to specify what is the graph that we will use. So, well, the graph is the graph proj that we have here. So, and as you might remember, this graph, it's already Networkx multi-graph. So this function understands the data right away. As the source location, so there is a parameter called source. So this what we will use now is that we use the origin node. So what was the ID of that node, and that will be the source. So we will put origin node as the source, and the target is the target node. And then, because we wanted to use basically the distance as the cost attribute, so if we take a look the edges.head, as you remember, we have this column called length in the data frame, so we can use that as the weight. If we don't specify anything, then each weight will basically have a weight of 1, and it will just, well, just find out the, well, do the optimization based on that kind of weights. So weight equals to distance, and that's basically all we need to have. And now, after this, what we will have when we execute it, no path to blah blah blah. No, well, that's good. Let's see. It could be that there is
Does the weight have to be the field name, because you use distance and in the graph for its length?
Oh yeah. Oh yeah. Huh. That's actually interesting. Let's take length. No. It might be now something to do with the topology of the network, because what I did here is that I took the centroid from the of the convex hull, where the earlier version in the yeah, maybe I try to do it exactly as here. So it might be just because the now the closest node is in a place which is not routable, so it's dead end, so to say. So that might be the reason, but let's see if I do it like I have done it here. So what I do in the lesson materials is that I don't take the centroid from the convex hull, but I take it from the bounding box of the edges. So let's see what we have there, and then we have the box centroid. So yeah, now we have a bounding box, and now we take the centroid from that. Now we should have the centroid indeed. And now what we want to do is to take this one again, and then this one again. Let's try now. Huh. This is interesting. Let's put it without the no path between blah 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 and blah blah blah. Well, let's do it like this. Just to get this thing through, I will now just copy and paste the nodes of the target and origin like here, so that we can understand what is going on. Okay, so there is something fishy happening in here, but the ones in the lecture materials should work. So now we got the root, and what does the root look like? So basically what we have here is a set of node IDs, and basically what we can do is that we can actually get the actual root out of here. Well, first of all, we could already plot this thing. So we can use the OX plot graph root like this. So there is a function called plot graph root, and basically if we run this function, what it will do is that it basically calculates the root. Actually now it takes a different root. Well, this is interesting. So, well, that might be just because they are similar. The distance from here compared to here, it's the same, and it takes the same different route than in the lecture materials, which took this one. But anyway, so what quite often it's useful that you are able to save this route on a disk, and it's really easy to get actually the route out. So we can get the information about the nodes. So extract information about the nodes that were along the shortest path. So what we can do is that row nodes equals to nodes dot log, and in here we just feed the route that was taken. And now what we have is that we have all this information now about the different nodes that we're taking when traveling the shortest path from A to B. And what we can do then is that we can actually visualize that and make a line string out of those points that we have. So what we need to do is that from Shapely geometry import line string. I'll also import the point. So that we can actually prepare that line string. And what we can do is that we can create the root and the line string out of the root nodes by specifying that line string equals to, and what we want to put there is a list of basically the point objects. So how we can take that is that we have the road nodes. So we have this geodata frame with these points, and then we take the geometry, so this column, and then we extract the values from that, and then we need to convert. It will return a NumPy array, and we need to convert that into list that this line string Shapely object can understand. And now what we have is this kind of line string feature, and what we can do is to create a geodata frame out of that. We can print the root line, and we can see that we have many coordinates in the line string. So let's create create a data frame from the line string. This is actually something that you need to do in the exercise, so it's good that you follow. So I will create an empty geodata frame like this. I can already specify that coordinate reference system is the same as the edges reference system, so that it's there available. Then I will create a couple of columns there, so the geometry column and then the OSM IDs column, so it might be good to have that information there as well. Yeah.
I have a question about the exercise before I have to do it.
Yeah.
Should the coordinates be in the C?
In the what?
They are in the ORC. The coordinates in the CSV is if I put them into Google Maps and they are in the C. In the exercise.
Then you have just put them on wrong direction. Like when you create the points, you should put point Y and X, point X and Y actually it is.
So are they like in the different order that they usually should be?
Yeah, so usually when that happens it's that they have somehow flipped, but I now need to check how they are.
You might have put them the wrong way into the file because I just copied them.
Yeah, well, I need to check. I think I put them on X and Y, but let's see. But I will put on Slack if there's something weird happening there. Yeah, but let's continue. So what we do here is that we put the row geometry. So let's put to the first row of that geometry column. There we can put this road line. So this shapely feature that we just created, like this. And now we should have geometry here, which is that geometry. Then what we can do is that we want to have the OSM, so the node IDs as well. So let's say row geom.log 0 and the OSM IDs equals to. Now we want to take the string out of the list of roads, out of the nodes, the road nodes, and the OSM ID column from their dot values. So now let's take a look. So now what we have two columns. The first one have the geometry and the second one has the node IDs as these kind of strings in there. So that's it. What can be useful is that we actually might want to know how long this route has been. So let's still calculate the route geom length in meters equals to road geom dot length. Yeah, and I missed, there's a typo. And now we have also, so the route seems to be 801 meters long. So now we have quite a lot of useful information in here. And basically we can plot this thing. So let's create a plot where we actually plot the route with buildings and roads. So this is the last bit. So let's see, plt.subplots. And then what we want to do, we want to plot the edges dot plot, and we want to plot it using the X that we created let's put the line width to 0.75 and let's put the color to gray. Then what we want to do as well, let's plot the nodes as well. X equals to X, marker size. So what is the size of the point and what is the color? Let's also put that into gray. Then what we want to do, let's retrieve the buildings. This is so quick to do, so I will do it. So buildings equals to OX buildings from place, and I take it from the place name that we had. So I do this, and then we want to plot it. So reproject it. So buildings equals to buildings dot to CRS. And what is the CRS? Well, it's the same as the edges dot CRS. Let's check what is the edges. So it seems to be UTM 35, so that's correct. Let's do it so, and now our buildings should have the same, and indeed we do. And now we are ready to plot those. So buildings dot plot X equals to X. Face color is khaki. And let's put some transparency to 0.7 and so on. And the last thing is that we want to plot the route that we just created. So the route geometry dot plot X equals to X, line width is 4, and let's put line style. So this is a parameter where we can actually specify that this is dashed line, and let's lastly say that the color is red. So now if everything goes right, we should have a map like this, which basically shows the route and the buildings and the street network of Kamppi region. So that's basically what I wanted to show you. Sorry it took longer than I thought. Not final assignment. So there is an exercise for this week as well, where you can practice a little bit what we went through. So there are two problems. So basically there are two CSV files. Now I need to check before you start doing that the data is as it should be. I will post it in Slack if there is something wrong. But basically what I want you to do, so there are some coordinates in there, so I want you to basically find out where those points are. So you should somehow be able to find it out. You might use maybe some geocoding or whatever, or just put them on the map and put some background map in there. Then what I want to do is that you should retrieve the OpenStreetMap data, which can be driven by car from the area where the points are located. Yeah, actually what we didn't do here that might actually cause some of these problems is that when we actually took the graph from here, is that we didn't specify. So there is a possibility to specify what kind of road data do you actually fetch from OpenStreetMap. Yeah, and that might be the case here. So there is this parameter called network type equals to drive, and this is the parameter that you can use to fetch only such roads that are drivable by car fetch only such roads that can be cycled or walked or so on. Now we fetched everything, and that might actually be the case. What was wrong in here? I might now try to run this again without these. Let's see what happens. But in the meanwhile, so you should find out the region where we are. You should basically plot the street network with certain color and put the origin points and the destination points on top of that street network, and that's basically it. And you should upload a figure of the map that you created and the code into your repository. Then the second problem is that there are 16 origin points and 20 destination points, and you should do the shortest path routes between all of these different points. So in total there are 320 routes, actually quite many, but basically what I want you to do, I might suggest using a for loop, looping over the points and then basically calculating the network or the shortest paths. And then what I want you to do is to basically repeat what we just did. So create a kind of geodata frame where you have all those route geometries from between different points, and then plot that map and then basically calculate the total distance of all the routes. And that is that's it for this week. So yeah, hopefully this will be fun. At least I had fun making it. Yeah, okay, now it works. Or does it? I think it did. Yeah. So it was just about missing this drive function here that it didn't find a way. So now we actually got the same result. It seems to kind of give different results as the shortest path, which might just be because indeed there are many different possibilities to take the shortest path in here, because it's so short, and well, is this shorter than this one? They seems to be quite close to each other, so that's why you might get different results. So don't worry if the map that you get as an output, if you do these, doesn't look the same as in the lesson material.